Cool. Sweet. So I'll also probably turn off my video in a second here. But thank you, Rich, and everybody else for having me today. I've been looking forward to talking about vector tiles and just kind of after my talk discussing with whatever y'all are interested in talking about. Yeah, gave a quick look at some of the last talks. Y'all are talking about some really sweet, big things. So I feel pretty grateful for being a part of this list. So yeah, video out. I will go presenter mode here. Cool. How's that look?
That's looking good.
Oh, cool. Thank you very much. All right. Great. Let's get going. Yeah. So as I said, I'm Sam Matthews. I work at Mapbox. Most of my day-to-day involves working with our tools that encode and decode this phrase vector tiles, and a lot of my work after that involves writing documentation and making sure that those tools are, at least to the best of my abilities, welcoming and do the things that we say they do in the easiest possible way for people to bring them over into their own stack. Yeah, and just a little quick blurb about Mapbox. I'll be talking about vector tiles today and some of our specifications and tools about vector tiles, but a lot of the work that Mapbox does as a whole is provide just like a full mapping solution for anybody wanting to put a map into their application, wanting to customize it, and then also providing a lot of back-end extracurricular services around like telemetry and location data collection, anonymized location data collection, important to note there. Yeah, so I'm just a little part of what is otherwise a large, wide team. Cool. So just a little overview before we get going here. I'm going to talk about like why Mapbox itself is using vector tiles, why it's a technology that has been quickly adopted over the past year and a half or past couple of years, why we're using them as opposed to old raster tiles. I'm going to go. I'll do my best to not bore you all with the anatomy and the spec about vector tiles, but since it's what I work on quite a bit, I have trouble not talking about it. But I put together a bunch of illustrations to make it a little more exciting than what a standard spec tends to look like. So yeah, we'll dive into the anatomy of a vector tile. Then following that, go into some encoding and decoding tools. I'll just share a bunch of links to a bunch of tools that are made for a lot of this work, and then kind of talk through a hypothetical pipeline that will kind of resemble like what Mapbox's pipeline looks like and what some other pipelines could look like. I'll introduce styling and how that comes into play. I'll talk about styles kind of throughout this entire presentation, but styles, despite being somewhat peripheral to tiling itself, are very important for vector tiles, or for at least making your map look pretty. And then lastly, I couldn't help myself but put together a bunch of GIFs of our recent 3D work just because they look really cool. So we'll go through some examples at the end, including 3D examples. Yeah.
Perfect.
So here we go. Yeah, and considering there was a 3D vector tile talk in the last month, I figured it would flow well. Yeah, so why vector tiles? So a lot of the work Mapbox and other mapping companies have been doing in the past years have been harnessing the power of WebGL. WebGL is a technology, at least WebGL specifically, in the browser that allows us to draw basically a bunch of little triangles when you go really deep into it, but allows us to quickly draw images and animations in the browser without having to worry about the DOM and worrying about bringing in images and yeah, so it allows you to draw quickly. Why? Another reason we're using vector tiles, it makes styling, or styles as I say, a first-class citizen. You'll see in a few slides how styles were kind of a crook in the old pipeline, and now we are allowing styles to be kind of the leader in our mapping software. And then lastly, and like importantly deep down, there's a huge cost savings in using vector tiles, especially when you're at scale. There's a time savings, like cost savings mentally, but also just like a cost savings when you're using AWS infrastructure to make sure that you're storing as minimum as you need. Yeah, and then also making the browser do the work for you. Cool. So this is just a little example just to like show a quick difference between like what raster tiles are and what vector tiles are in this little animation, which I hope you're all able to see. This is just using open layers. It's an open mapping, open source mapping platform. It has a rotate function, and if you're pulling in raster tiles, which are images, you don't have the opportunity or the ability to really update that image other than just like translating it and rotating it. So you see this example here with like the text basically being upside down, which is not terribly useful, especially when you're trying to like see the world from a different perspective and learn about it. So with that in mind, vector tiles and WebGL have enabled us to basically redraw the map based on interaction, based on basically any movement without having to worry about images being static. So you can see in this example here the map rotating 100 degrees in Madison, Wisconsin, which is where I went to school, if there's any Badgers there. But yeah, you can see that the labels stay in the same direction, and everything kind of updates itself based on what would be a user interaction here. A couple more examples of some of the things that vector tiles and styling allows us to do other than raster styles didn't. You can see here in Mapbox Studio, this is just one example of editing a style for vector tiles and their styles. But in this GIF, you can see just like changing the color updates the map immediately without having to re-render images. And so that means we don't have to do anything on our servers to re-render images and serve them to you. So there's fewer API requests here. And it's a lot smoother interaction and user interface. And then the next GIF is kind of like the icing on the cake that really sold me on the difference between the raster tiles and vector tiles. This is showing us actually me taking the lake color information and changing it based on zoom level. And so instead of having to bring in new images, a user is able to change things. I mean, this is just color for one example. As you zoom in, the color can change, but you could do wacky things like change the font or the typeface as you zoom in, or the thickness of the stroke on a road, or, you know, like opacity from 0 to 1 as you get closer and closer. So it really allows us to build a lot stronger animations and more realistic like world representations. Well, except for water being gray or red in this case, not very realistic there. Yeah. So taking a step back from the somewhat pretty examples, I just want to kind of show a quick flow chart of like what making raster tiles looks like and what making vector tiles, or what making a raster map looks like and what making a vector tile-based map looks like. In raster tiles, or when making a raster-based map, on the left side here, you need a data source. Always need a data source, and you need to know how to style that data source. And then there's these really bulky, very impressive tools that were built, Mapnik, one of them, that essentially have like a giant internal structure or mechanism that's made for image rendering. So it takes styling information from XML, it knows what layers exist in data, and it pipes out these images. And those images can be put up onto storage space, and then when you load your map, it grabs those images and stitches them together. So you can imagine if you needed to update your style, you kind of have to go back all the way outside of this tiling machine. I'm going to keep it a vague tiling machine for now. Update things and then remake all of these images. So that is not only expensive in time and CPU, you need to effectively duplicate the world and its tiles as you make style changes, which if you're styling an entire planet down on Zoom 20, you've got like hundreds of millions of tiles to recreate, which is a lot of storage and a lot of CPU power.
And would that Sam, would that be would the exception to that be like just modifying the color map?
Yeah, exactly. So you could modify the image itself. Is that what kind of what you're asking
Yeah.
there? Yeah. So I mean, you could modify the true, like the PNG or the WebP, whatever format it's in,
Hmm.
if you wanted to. But a lot of these tiling machines are made to take in styles, take in data, and spit out images. So if you were editing the image itself, you'd need to do some other fancy work that I'm not familiar with.
Right. Okay.
Yeah. And so the alternative is this vector tile pipeline, where data is still a first-class citizen, and it's kind of one of the most important things here. But you can use that same tiling machine, at least in an example that I'll show you later, to create vector tiles. And so these aren't images that are coming out anymore. These are like binary encoded protobufs, which I'll talk about in a little bit, that come out and maintain or contain actual point information from the source data itself. And we use a library can then take a style and these tiles and apply it at runtime when you're loading it in the browser. So you can imagine you have this source set of vector tiles and your data is not updating too much. You can apply any sort of style you want to this set of vector tiles. And so it allows you to make an infinite number of styles for the same tile set without having to go back through that map tiling machine process. And so those styles don't just like come out of thin air. There's a lot of things, as I showed earlier, Mapbox Studio is a thing is a tool built to edit these styles. And there's a number of tools out there. I think Google just released one, and Map10 has one as well. So that style editor is a good, quick way of updating your styles. And then through the rest of this talk, I'll probably reference a group of vector tiles as a tile set. You can also reference a group of raster tiles as a tile set, but for the duration of this talk, I'll be talking about vector tile sets. Cool. So that's why we're using vector tiles. But what is a vector tile? It's a loaded word. This is probably the densest description I could put together about what a vector tile is, so don't feel like I'm intentionally being overwhelming here. So a vector tile is a binary encoded gridded square containing layers, features of vector coordinates, and attributes unique to those features. And we'll kind of break that sentence down here in a second. So yeah, diving into the anatomy and a lot of the words I just said. So the actual file format of a vector tile is a Google protocol buffer, which is a very loose specification put together by Google that allows you to basically have key value pairs in binary format. And so if you know JSON, if you know about JSON, there's a key and a value very similar in a protocol buffer, except it happens to all be down at a binary level. So a lot of the ways to work with Google protocol buffers is to actually have pointers and strings and running at the C++ level, or if you're very fancy, you can do some JavaScript work there as well. An anatomy of a vector tile specifically, it calls for these things that we refer to as layers, which is also a very loaded word. So if anyone gets confused of my usage with layers, feel free to speak up. I get confused when I use the word layer too much as well. In these layers, they can have features, which basically relate to geometry. So you can have a layer of land use, and that land use can have shrub or forest or like tundra features. Those features have keys and values and tags that refer to the attribute information. So something like a tundra would have its geometry specified, and then would point to a specific part in this protocol buffer that calls it tundra versus forest or versus snow. So now come in the illustrations because specifications get pretty dry. So I try to make them a little more exciting here. So what you're looking at right now is a single vector tile in this kind of three-dimensional space. But remember, it's just a binary encoded file. This vector tile has 4 layers. There are mountains, there are buildings, there are forests, and there are campsites. Layers in a vector tile are very similar to like layers in a KML file, or if anyone's worked with the NB tiles format. If you look at like if anyone's familiar with GeoJSON, the layers don't really exist in GeoJSON world. The GeoJSON can be like one giant feature collection, so it can have a lot of features, but you can't have multiple feature collections in a GeoJSON. So you can kind of look at this vector tile as 4 unique GeoJSON feature collections, those being mountains, buildings, trees, and campsites. So digging into one of these layers, each layer has features, and you can see that these features are pointed specifically on a grid. Can you all see my mouse or my cursor?
Yes, yeah, that works well.
Okay. Yeah. Cool. I'll probably like point to some things. Yeah, so let me know if it's a little unclear.
You can use that. You can use that swooshy thing at the bottom too to make it a little.
Oh my gosh, that's super fun. Okay, cool. Now you get to all watch me play with this for a little bit. Okay, cool. Yeah, so a vector tile itself is actually not geographic at all. It has a grid structure that starts at the top left corner, and that is coordinate 0, 0. As you go to the right, you increase in the x dimension, and as you go down, closer to us on the screen here, you increase in the y dimension. So you can see these features are encoded to specific points on this grid. So if you go, we're going to go 3 to the right and 1 down. And so you can kind of start to see that you really actually lose your geography here, and each feature is only built into this really relative grid. So it has no understanding of other vector tiles and their grids around. And so each of these features, I just colored them red here. We don't have to say that they are supposed to be colored red because they are just data. But they have pointers to things. They're sort of dictionary encoded, and I'll go into what that means in a little bit here. But 2 features have this number 1, and that number 1 is pointing to forest. So instead of both of these features each saying forest, we just like encode a very small integer to point that way, and then 2 points to grassland. So we don't have to repeat strings as you increase in features. So as I said, one vector tile does not really understand what's going on in any of the other vector tiles it has. So as you can imagine, in our previous example, we're really lucky because we have 3 features that only exist in this vector tile. But the real world is very complex, and we have features that span over many vector tiles. So this example is just of a polygon that exists in, I guess, 5 different vector tiles, depending on the zoom level you'd be at in your map. And to encode this, there's a lot of like very magical, and I hate using the word magical, but like this is truly where I don't understand how computers work. But there's a lot of algorithms out there that are made for clipping geometry to the boundaries of a vector tile. So if you have geometry that is greater than the extent of this vector tile, we have to clip it down. So we go back to a single tile, and we actually kind of have this new feature. And if you can see, as we went back there, a few new points were added. And you've got a feature that basically runs along the edges of the vector tile here. And that might be a little confusing because now we've actually changed the geometry for good. And yes, it is changed for good. We no longer have the ability to reference this feature to its previous original style. So this piece over here no longer knows that it was part of this piece here. And so I think it's an important note to make that vector tiles are not meant to be geographic data storage formats. They're meant to be vector data storage formats. So we lose all of our original geography here, and we have to rely on the mapping libraries to do some special kind of illusions to make it look like it's an original geometry. So when you're rendering a library, you'll come back here and everything is put next to each other so it looks like it's an original piece of geometry, where in fact it could be multiple polygons all just happening to align very nicely. So there's a lot of algorithms that make sure that we don't lose alignment there that happen in our vector tiling tools.
But I mean, but they do, but they, Sam, but they do. I mean, they do obviously know that they're part of the same feature, or essentially, right? I mean, through the IDs and stuff that you have.
There are definitely ways where you have to, so an ID is not necessarily required in the vector tile specification. So in some libraries, if you wanted to hover on this feature and get to the whole feature, you would actually just see the square boundaries of a feature that you're pulling out, unless you do some special work to find the similar IDs and create a new geometry.
I see. Okay.
But that being said, your vector tile is just specific to this grid. So you can have geographic coordinates that exist in between this grid, but in order to simplify into a gridded vector tile, you have to change geometry slightly. So if you're pulling out geometry from a vector tile, it's not going to match as exactly, or it's not going to be a perfect match from your source geometry.
Okay.
But our eyes are not perfect, so we make sure that grid is smaller than what we can actually perceive. Yeah, so here's just a quick example of how properties are encoded. On the left, I know it's a little small on the screen, so I recommend going to this page after the talk, the mapbox.com vector tiles/specification, and you can play around with all these interactive examples. But similar to I was saying how the shrub and grassland were encoded without having to be redundant, you can see as you hover on Hello World, on the right side, the feature is pointing to a count, or it's pointing to hello for its key value, and then it's pointing to what is a unique value in world. Sorry, my talking was not aligned with the GIF time there. It's hard to do. Cool, and then this is an example of how geometry is encoded. There are these special commands called move tos. So you can imagine you have a pen and you're drawing on like a gridded piece of paper. There are commands that tell you to move that pen. There are commands to tell you to move that pen along the piece of paper. And then there are pens that tell you to like close a path back to the previous point. So it's move to line 2 and close to, or close path. Yeah, and so this is how these algorithms actually draw along this grid.
And what was the gray? What was the gray? What's the gray significance of the gray?
Great question. So if I go back to this kind of example, I'm not really showing that gray here, but what at least Mapbox does, and this is not a requirement of vector tiles in general, we encode our own little extra buffer around. So the white here is actually all you'll ever see when you're rendering it in a library. But the gray is just kind of a buffer to make sure all of these features are overlapping precisely. And yeah, so it's just kind of a little safety net.
Halo, yeah.
Yeah. And then at the end of this is showing there's a red line and a blue line showing that things have to be drawn in clockwise or counterclockwise direction to in order for us to understand if something is a whole, if we have a donut geometry, or if it's a unique feature that just happens to overlap. And so you can see here as it renders, since it was in counterclockwise form, it is a whole. And I saw this is the last slide about the specification, so if you've made it this far, congratulations. But yeah, so geometry in the end, you can kind of see similar mentions to line 2 and move 2 here. If you go deep down into a protocol buffer, you'll see that all of our geometry is encoded as 32-bit unsigned integers, and that string can be however short or however long it needs to be for a feature to exist. And I recommend going into our documentation more to learn more about this actual stuff. If I were to describe it here, I would do it poorly, and I don't have time for that. So all of these instructions have to come from somewhere. We at Mapbox have put together a specification for encoding tiled vector data, nicely called the Mapbox Vector Tile Specification. It's not the only spec out there, but it's definitely a growing one and pretty widely used amongst mapping libraries. I recommend going and checking out the actual spec if you're really into reading spec language. But yeah, it's ever moving. There's always discussions on how to improve it and how to expand it, but also how to make sure that it is or making sure that our data are small enough to transfer over the web. It recently went into its 2.0 phase, or 2x phase, and I really like this slide because 1x was basically an experiment. This is showing the actual specification, the written specification of the Mapbox vector tile. So last year at this time, this is what the spec looked like. So you could, it was kind of the Wild West. You could put whatever you wanted into a vector tile as long as you had a thing called a layer and a feature with geometry. As we grew our tools and found the right and wrong way to do things, the specification got much more specific. I hate to use the word specific in a specification, but that's kind of why it's there. And so you can see literally just on length of page and words written, we have more examples of how to encode geometry and how to encode keys and values. So yeah, I recommend taking a quick read unless you want to go deep. The original, yeah, go for it.
Well, I was just going to say, is everybody using, pretty much everybody using 2, or is there like a ton of stuff written with 1, or?
That's a great question. Everything at Mapbox is using 2 now. I know MapZen has a Mapbox vector tile encoding Python library that recently moved to ensuring everything is 2.0 compliant. And really, like the hardest thing here is making sure geometry are OGC valid, which is the beginning of this slide here. Yeah, so geometry could have been, I anthropomorphized geometry in this slide, and it's just like a crazy jumble of anything, and it could be encoded in a vector tile. In order to improve our rendering tools, we needed to make sure geometry were much nicer. So the 2.0 spec requires all geometry to be OGC valid. And I'm not going to go into examples of what are invalid geometry, but think of things like bow ties and just like lines that are sharing the exact same dimensions, but they should be a polygon. Yeah, so we need happy, nice Tetris-like pieces here. Yeah, okay, so that's the end of the spec, at least as far as I think people want to hear about today. So I'm going to go through some encoding and decoding tool examples, and then kind of dive into styles themselves, which is actually a whole other specification, which I personally don't know as well as the vector tile spec. So I'm going to lightly cover that one and just relate it to vector tiles. And then I'm going to just kind of do a quick walkthrough of an example pipeline from source data to rendering a map on someone's computer and what that looks like. Yeah, just some examples of encoding tools. I, in previous slide, had a thing called a tiling machine or vector tiling machine. I usually use Mapnik in this case. Mapnik is a C++ library that's been around for a long time and was originally developed to render images based on XML style queries and source data. It's since been updated to also spit out vector tiles. So I recommend taking a look. If C++ is scary, which it is for me, there's a Node.js port, which I'm very grateful for. So I recommend taking a look at that. Tippecanoe is another command line utility that is developed at Mapbox, but it's specifically for ingesting GeoJSON files, like really, really big GeoJSON files, and actually spits out an MB tiles file, which is basically a big collection of vector tiles. GeoJSON VT is a JavaScript library, Node.js library, that is in pure Node, pure JavaScript, that decodes and encodes vector tile, or it takes GeoJSON and encodes it into vector tiles. This is actually part of the guts of Mapbox GL.js. So I recommend taking a look at that. Vladimir, who wrote the base or put together the origins of this library, kind of spooked the world and got everyone a little excited when he clicked and dragged like 100 megabyte GeoJSON file into a browser and it rendered essentially immediately, which has kind of been a dream of all of us in the past a few years to be able to do that. So GeoJSON-BT has been a pretty fun library to work with. And then lastly, I had mentioned just a couple slides ago, MapZen is also working on, they have their own vector tile encoding library that's written in Python that writes Mapbox vector tile spec compliant tiles. So take a look at that as well. They're very actively maintaining that. Yeah, and then the decoding side of things, once you have a protocol buffer, you need to be able to know what to look for in it. You need to be able to parse the information so you can render it with WebGL. VectorTile.js is kind of the alternative to GeoJSON-BT. It takes protocol buffers and converts them into a JavaScript syntax that represents a vector tile geometry. VectorTile, very poorly named, is a C++ library that decodes protocol buffers into vector tile information. And then Mapbox GLJS, which will kind of be the basis of the rest of the talk from here, is our WebGL rendering library that uses a number of the tools that I've mentioned just above to ingest protocol buffers that are vector tiles and render them on your browser. So I list it here as a decoding tool, but it's truly a WebGL rendering library that happens to deal with mapping information. So into the style specification we go, and hopefully not too deep. Yeah, so like I said earlier, vector tile sets need, in order to render something, they need a style specification to tell them how to, the library needs to know like what color to make shrub land use or what color to make primary roads and how thick that road should be. So we need to be able to rely on this style changing or not changing semantically. So we have the Mapbox style specification, and the style spec, this is just an example, the high-level example. It references where like its glyphs and its fonts are coming from. It references these sources, which are actually the vector tiles themselves, where they're coming from, and then layers. Like I said, it's a loaded word. Layer and style specification means something different than layers and vector tiles. So we'll go into that layer just here. So a layer in the style spec can reference a layer in the vector tile, but it doesn't have to be a one-to-one relationship. So this example is just showing our new style, saying like I'm going to style water. I'm going to grab it from our Mapbox streets tile set. That tile set has a layer called water. I want to go into that layer. I want to render it as a fill type, and I want that fill to be this color. So this is probably a blue hex color. So a very simple example, but it's like I'm going to take all of the information from this layer. I'm going to assume it's all a polygon, and I'm going to color it blue. I'm going to fill it blue. I'm not going to add a stroke to it. I'm just going to fill it blue. So this is what the spec does. So if you've ever used Mapbox Studio and downloaded your style from it, it's really long and complex. So writing like this JSON file for a style is pretty cumbersome, which is why tools like Mapbox Studio exist to make it a little easier for the user. Cool. And now I'm going to quickly go through an example pipeline. From beginning to end, everything we've just talked about, I'm going to quickly show you kind of how it exists in Mapbox land. So yeah, first things first, you have source data. We, for Mapbox Streets, use OSM, OpenStreetMap, for a lot of our base map source data. So we have a lot of PostGIS queries that are happening internally to create vector tiles or to turn this information into usable geographic format. And then we have this very loosely defined tiling machine again. Mapbox internally uses Mapnik and Mapnik when you're uploading to Mapbox Studio. So everything that I just showed you, everything that we use internally is an open source project. This tiling machine needs to take in data and figure out, like, am I going to make a zoom level 2 tile? Am I going to make a zoom level 3 tile? I need to figure out where that tile exists in the X and Y plane of the world. And then based on the source data, it can pyramid all the way down. So if people have learned about raster tiles in the past, vector tiles are very similar, where at zoom level 1 or 0, you have 1 tile. And then as you increase your zoom level, you increase the number of tiles needed to represent the world exponentially. So you go from 1 to 4 to 16 and onward. So we call that a pyramid. And for each tile in that pyramid, we create an individual tile and push it up to S3. So S3 is just a storage space hosted by Amazon. And if you're looking at your own computer file systems and you're looking for a specific tile, we literally just put those tiles in a file structure that matches the X, Y, and Z, or the Z, X, Y coordinates of the tile. So that's our only way of knowing where in the world this vector tile actually exists. Because as I mentioned before, vector tile coordinates themselves are represented just in a grid that doesn't know other grids around it. So that's the rendering, the encoding side of things. When a user goes to load a map on their computer, they get a map style, as I mentioned just in the last slide. That map style needs to figure out how big the screen is and like where in the world this computer or this map should be rendering. So it literally goes based on screen coordinates and where the library you've used, Mapbox GLJS, for example, what zoom level you've set. So we get some calculation there to kind of create our own pyramid on the browser side of things. The style knows which tile set we're calling, so we go through an HTTP request. That HTTP request is able to point back to this storage space on S3 based on a Z, X, Y that we've calculated here. We get this binary file. It is decoded using vector-tile.js if you're talking about Mapbox GLJS or another library. And then you go through those styling properties like I mentioned for water. It's like, oh, we see the water, we want to take the water information, apply that, and then we render it onto the map. Yeah, so feel free to add more questions or ask questions there. I'm happy to go back to that slide. And I'm going to try and quickly get through the rest of these. I see that I'm nearing 35 minutes, which is a little over time. Yeah, so just kind of to wrap everything up, vector tiles and WebGL allow for larger data sets and powerful visualizations. And as I couldn't help myself, I'm going to just have a few GIFs here. This is showing all the bridges in the United States. And a few years ago, none of us were able to show this many points on a map unless you made your image tiles in advance. But these are being loaded on the fly. Here's just a very slow zoom out to show that like we don't have this idea of a zoom level is much more loosely defined now with vector tiles. You don't see new images load as you get further and further out. We can just update our information as we move. And then lastly, recently introduced data-driven styling. So as you load information onto the map, you can style it according to the properties that these geographic features have. So this is showing ethnicity in San Francisco and styling based on the properties that each point has and giving it a color. And then I'm going to do my best to not talk too much about 3D, mostly because I didn't do the work here, so I would be the wrong person to talk about it. But we recently introduced 3D rendering in Mapbox GLJS and the Mapbox style spec, and it's allowing us to take building heights and show them just on a map. You can go from version 0.26 from Mapbox GLJS to 0.27, and all of a sudden you have the ability to show 3D features. Not only can you do building heights, people have been doing interior extrusions. So this is like very defined field museum. I guess not very defined. It's pretty generalized in Chicago. But people are starting to think that like Mapbox GLJS could be used for things like CAD, like things that CAD does. So you can actually start doing building development. And then lastly, I saw this example a couple days ago and liked it. This is admissions in London, and you can kind of see the heights and the density, and kind of notice that all of the information here is very unsurprisingly correlated to roads. And I liked kind of my GIF shows latency a little bit, but it shows stuff loading in its actual square tile, vector tile coordinate. And then lastly, we're getting into the game space pretty surprisingly. We just released a Unity SDK. If anyone is a gamer or game developer out there, and this is an example Camilla put together. She is loading our vector tiles, putting them on a mesh, which Unity allows you to do, and then adding extrusions based on the work that I just showed in the last slide, and driving a pretty sweet old car. Yeah, so I recommend going and checking out github.com/mapbox/awesome vector tiles. This is a curated list of just like sweet projects, sweet examples inside and outside Mapbox that show the usage of vector tiles. Yeah, and I urge you to go back through my slides, check out some of the links. Vector tiles are really complex and they take a while to learn if you really want to get into them. So feel free to send me information, send me questions. Yeah, happy to help. That's all I got.
Awesome. I always wish you could like somehow clap, on a webinar, but
I appreciate it.
That was really good. Just really very clear and exactly what we needed. I think a very good level for us, I think, in terms of the technology. And
Right.
so, I got some questions, but before I ask those, I think I'll just open it up. And let's see, everybody is muted. If you, I see a // in the chat.
Nice. Do you want me to keep this screen up, or should I?
Yeah, keep that up. And so, folks, either if you can't unmute yourselves, just chat. And actually, hold on a second.
Yeah, I can see the chat here too.
Yeah.
So if you want to add,
I unmuted everybody, so feel free to ask a question, folks.
Perfect. You know everything about vector tiles.
Okay, well, I'll ask a question then.
Great.
So when you, so let's say you have a really detailed, coastline. I think actually your kind of last example showed that. So when this builds your vector tiles, it's obviously doing, with these different resolutions, it's doing some kind of line simplification algorithm or something like that. Is that what it's?
Yeah, so that's, I imagine you're talking about.
Well, yeah, your zoom out,
exactly.
Obviously you for vectors, since it's still vector, you have to reduce the number of points, but you're trying to preserve the actual shapes and complexity as much as you can, right?
Actually, you asking that question makes me realize I didn't really describe the similarities between raster tiles and vector tiles. So vector tiles aren't just like one flat set for the entire world. What's actually happening here as you zoom out, it's loading new protocol buffers over the layer.
Like I just saw Long Island actually change its, actual geometry, and then there again, you can see it.
Exactly. So that's not the same vector tile updating itself. It's a new vector tile being drawn.
Right.
That's just simplified in our actual creation process.
Right.
But what's nice is that it can happen kind of elegantly and smoothly instead of loading a new image on top.
Yeah.
Yeah, good question.
So, were there any, actually that's kind of probably too far down the rabbit hole, but I know there's like different ways of handling that, and I was wondering if you guys came up with anything new, or are you using the sort of existing algorithms for doing that? But
for the actual simplification?
Yeah, it's kind of down the rabbit hole, I guess. But.
Yeah, I won't be able to even go very far down a rabbit hole just because a lot of that is kind of in math land and algorithm simplification clipping land. And so I know we use a VATI algorithm for that simplification, but that's just kind of a buzzword in my head. I can't really talk too much about that.
Okay. It's not really related to vector tile that much anyway. So anyway, there's a question here in the chat.
Oh, cool. Sorry, I missed that.
Can you see it?
Your example has 4 layers, but can there be more in a single tile? Is there a limit? Great question. There can theoretically be an unlimited number of layers. I believe, okay, sorry, I'm just trying to formulate the best way to respond, or best way to like knowledge share. Yeah, a vector tile can have any number of layers. Mapbox Streets, for example, which is like a pretty beefy tile set, has I think like 20 to 22 layers. If you upload just a GeoJSON file to Mapbox Studio, that'll have a vector tile set of just 1 layer. But thing that I didn't mention is that you can actually composite different tile sets into one tile. So say you have Mapbox Streets and you want to add your own custom data that you've uploaded as a tile set from Mapbox Studio. On the request and on our servers, we turn those two different tiles into one tile before we send it back to you. So if you have streets with 22 layers and your custom tile with one layer, you'd end up with a vector tile of 23 layers.
Hey Sam, before you answer the next question, can you switch to a static slide? I feel like I can't stop. I'm like the cat with the laser pointer.
I realized that I was actually kind of just staring at it too.
Okay.
Cool. Looks like we got another question here. Are there plans to support multiple/custom projections within Mapbox? There are. Okay, so I'm having trouble figuring out which route I want to answer this question. There are not plans to support custom projections, but that doesn't mean vector tiles don't support custom projections. And I'm actually relatively unfamiliar with this, but I'm going to search. Can people see my screen here?
Yes.
I actually just found this example on our website the other day that AJ Ashton put together. Oops. Of the North Pole in a non-Web Mercator projection. So this itself is a polar projection. I imagine a lot of this was like one big hack. It wasn't a button on Mapbox Studio. So I wish I could answer that a little further, but if you send me an email after this, I can point you to how AJ put this together.
But it sounds like the key thing is that that you certainly allow it though, right?
Yeah. Vector tiles itself, in the specification, we do not specify. We don't say what projection any of the coordinates need to be from.
Yeah.
Cool. We got another question here. So tile sets exist and can be combined. Will all clients understand how to deconstruct and display them? I imagine not, unless they are developed to combine a style and an equivalent tile set. Neither of those really are much without the other. But I'd be curious to know if there's like an example client library that you have in mind. But like Mapbox.gl definitely knows what needs to know the specification and how to decode and how to apply a style to it. So that's all part of the library.
Yeah.
I hope that answers the question. Feel free to say it does or doesn't.
Is that is that a proprietary and that's a open source or? Yep.
Yeah, it's all open source.
Okay.
Mapbox.gl.js is this is going to go a little beyond my knowledge, but WebGL decodes all of this, or we decode all of this into WebGL shaders, which are buffers, and those shaders need to know the specification and the data that are coming their way. So there's a bit of validation on the Mapbox.gl.js side of things. But that's all open source.
And you're making, I mean, how do you guys make, what's your business model for this stuff? You make your money serving the vector tiles, or?
Yeah. So we make money in a couple of ways. One general customer base, and the largest customer base are just like users such as ourselves who want to put a map on a website, and in order for that map to work, it's an API call to our servers. So as you collect more and more API calls, that's how like our charging scheme works. For larger clients, we also have services outside of tiles themselves. We have a geocoding service. We have a directions service. Clients also, we also rate based on API calls to those as well. We have some larger clients that are kind of like in a secondary customer that are in like more of a experimental mode. Like they're joining forces with us to like see where we can put mapping and like how we can expand, like put maps into a new realm. So like gaming is something that kind of came out of nowhere. but now we have like an entire gaming team looking at how to kind of turn Mapbox into potential, not turn Mapbox into a gaming platform, but turn Mapbox APIs into an accessible part of other gaming platforms. Yeah.
Okay, cool. Hey, I wanted to ask before too, I assume your 3D, you saw the last time we had a presentation from AGI,
Yeah.
not 3D vector tiles, and they have a specification, so I assume yours is a competing specification, but I mean, still open, but, or is it?
I'm really happy you asked this question because I expected someone to ask this question just because of like the time of those two presentations. I would definitely not list our specs as competing specs. So I was talking to Lucas, who is one of the lead developers of Mapbox GLJS, just because other specs kind of go beyond my knowledge. And he described Mapbox's vector tile specification as one very specific to rendering 2D layers with WebGL. And so expanding it into 3D is kind of we're not using WebGL in a standard WebGL sense. It's like made for 3D rendering. So the way we've made our 2D surfaces really beautiful is by reducing our ability to do a lot of 3D work. And so we've kind of hacked in, you know how you draw a 3D square on a piece of paper. A lot of our 3D work is kind of just like very simplified into that.
I see. Okay.
With our GL library. If we wanted to push our 3D limits, we would have to do a full rewrite and a full reconsidering of the spec. And I don't know much about the other spec other than the presentation, but it would be silly of us to come up with a competing open spec, especially one that's so well defined.
Yeah.
Yeah.
Okay, cool. I had one last question, like going back to something you said earlier. You were talking about Vladimir, his 100 megabyte GeoJSON dumped into the browser. If he actually drag and dropped like a 100 megabyte GeoJSON into the browser, did that then sent like that transmitted back to your server, created the vector tiles there, and then
sorry, cut you off. Finish your question.
Well, no, I mean, you know, so I'm just wondering where the tiles were being served from in that case.
Yeah, that's a great question. So in Vladimir's example, I'm just going to go to the GIF of it because I believe it's just on the Mapbox Geo. Typing while people watching you is always a little stressful. Yeah, so I'm just going to let us watch this example quick. I'll let it restart. Oh, here, it's up here. But basically what's happening here, GeoJSON VT is not, as someone clicks and drags into this library, they're not creating a vector tile set in Mapbox land, so it's not doing any requests to a server. But it's it's like taking this JSON format, GeoJSON format, and constructing GL shaders from it using GeoJSON VT and adding it as a source with Mapbox GLJS. So no, it's not creating a new tile set in a storage space. So like if he reloads this page, it's gone. But it's it's just adding it as a new shader or a new layer into the map without having to essentially parse each JSON, each piece of the JSON as true JSON. He like goes straight into buffer form.
So it is using the tile spec though. I mean, it is
using the tile spec. Yeah. So
but it's just not. There's no reason for it to go to the server just to come back with it. Yeah, I got it.
Yeah. I wish I knew more about the stuff that's going on under that hood, but it gets a little complex.
Yeah. Okay. It looks like we have maybe one last question, a long one.
Cool. Here, I'll also get off of this GIF.
Okay. Thank you.
Use the vector tiles only to mapping libraries that can display them. Data in those tiles can't be used so that it tools to do additional analysis. So this is a great question, and I don't know if I have a perfect answer for it, but I'm going to kind of talk through what's in my mind when I think about this question. So people who are not able to see the question, Dana asked if we lose our source geometry when we're encoded into a vector tile, and we can't really use vector tiles as a geographic data storage format, like, do we can libraries that are meant for things other than just displaying information use them still? And then are there other libraries that are going to pop up that might want to, or maybe other specs that pop up that are intended to store original source information? So I'm going to answer the first part of that question first. So does that limit the use of vector tiles only to mapping libraries that can display them? I think vector tiles will always be limited to the libraries that display them, at least as far as wanting to put a map on a page. But the cool thing about a vector tile is that the spec doesn't say how dense your grid should be. So working with the browser, we have to be very conscious about making a file as small as possible. So we have to kind of like play this balance game with like how detailed can a vector tile be at a certain zoom level, but how simplified can it be without having to load all of the original geometry. So when using Mapbox GLJS, yeah, it's definitely not the best way to look at vector tiles as a storage format. But if you're not talking about rendering visually, vector tiles can technically be a storage format. It's actually a large part of how our geocoder works, is using vector tiles that are like much more dense because we don't have to worry about sending them over the wire. And if we are doing geocoding queries, we're able to know where in the world something exists, and all we're doing is actually we're using vector tiles for our search process, but we return the actual information from OSM or from wherever the source data come from. So they end up being kind of an intermediate data store. So yeah, I think that I don't know if that perfectly answers all of the questions there, but in the analysis sense, I think analysis can still very elegantly exist with vector tiles and rendering libraries as they currently exist. To the naked eye right now, if you can't tell the difference, and if you're looking at like very, very micro mapping, you can render vector tiles down to very deep zoom levels to the point where like you can encode more information than the GeoJSON spec even allows. So if you have a very low level zoom level of the vector tiles, you'd still essentially retain the necessary source information, unless you're doing like individual mushroom mapping, which would be awesome. But I don't think vector tiles would be the right way to go.
All right. Well, it's 4:02 here on the East Coast, so thank you.
Fast.
Yeah, it did go fast. That was super cool, and thank you, Sam, for taking the time to present to us. As this was recorded, and there's a lot of, as I mentioned, there's a lot of folks who wanted to watch this, including a lot of our folks in USGS in Middleton, Wisconsin. A lot of those guys are University Wisconsin grads, and they will be badgering you with questions.
Great. Now we all have to leave now that a pun was thrown out.
Exactly. All right, so have fun at your holiday party. And everybody, just one last thing. Next time we're going to meet 1 week later than we usually meet because the second week in January is the ESIP winter meeting. So, but you'll get the announcement. Don't worry about it. Just we hope to see you back then for a talk on the Google Earth Engine, which is another cool thing. So again, thanks, Sam, and take care, everybody. See you next time.
Thank you very much. Cheers, Rich.
Bye.